Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on solving equations and finding real roots of real functions. And so far we have discussed the general lemma of root bracketing, and the idea was that the sign of the function should change if it's a continuous function and the sign changes over the two ends of the interval. We are guaranteed that we at least have one root, and we call the interval basically a bracket for the root, which means that there is one root in this interval. That's the meaning of root bracketing. We looked at the bisection method and implemented it in Java. And also we extended the bisection into trisection method, where we divide the root bracket into 3 pieces instead of 2 pieces. And then we also looked at the secant method, and we looked also at the Brent's method. And there are 2 methods left. One is the Newton or Newton-Raphson's method, and the last one is the generalized Taylor method. Now, to recap, we said that the behavior of the function locally around the root could be either a tangent, where it could be either a simple behavior, which we call it a simple root, or it could be tangent without changing the concavity of the function. So f double prime remains the same on both sides in a neighborhood around the root, and we call it an even root. So the function is tangent. And finally we said that the function could in fact be tangent, but the concavity can change, or f double prime changes sign, or f double prime is basically 0, which is called the stationary point of inflection. And in this case we have an odd root, a root that is not simple, which means the first derivative is still 0, but the second derivative is also 0. So the order of the root around the Taylor expansion around the root should be 3 or 5. It cannot be 1. But if f prime is greater than 0, which means the function is not tangent at the inflection point, we have a non-stationary inflection point. And in the non-stationary inflection point, we in fact have a simple root. So the order of the Taylor expansion is 1. All right. Now regarding the bisection, it was very simple, and what we mentioned was that unfortunately bisection is always guaranteed to converge to the root, but it's not very fast. All right. But then the only case that the bisection may fail is when the function is actually tangent. We have an even root, right? Similar with the trisection method, the same thing, because the trisection and bisection are just based on a binary search or ternary search. And then we said that, okay, if we want to improve upon this, we can use the secant method. Now in the secant method, what we said was that we start with the bracket for the root x0, x1, and try to come up with a recursion that takes into account the behavior of the function. And the simplest way to do that is connect the 2 endpoints of the function at x0 and x1. And because x0, x1 is a bracket for the function, we know that the values of the f have different signs. So when we derive this line from x0 to x1, this line is guaranteed to cross the horizontal axis at some point in this interval. And this point then is guaranteed to be closer to the root than both x0 and x1. Okay, so by doing this, we can build a recursion. So we said that at some point, if the bracket of the root is xn minus 2, xn minus 1, we draw this line, find the crossing with the horizontal axis. We call it a better approximation for the root, xn. And then we repeat the secant method in the xn minus 1, xn interval. Now the problem was that if you look at the secant method. The problem here, specifically in this example, in this function, that when we continue with the recursion in the x minus 1 and xn, this interval is in fact not a bracket for the root, right? The root is here. So if we continue with the secant in this region, we end up with a root that is actually farther away from the root, from x2. So the distance of xn to the root is much smaller than xn plus 1 to the root, right? So this is a problem, and so far we did not address it in the code, but we try to go and address it in the code. And what we are going to do is that if we start with the bracket x0 x1 and then we want to make sure the recursion remains in this interval. So each time, in fact each step of the secant method applies to a valid bracket. That's the point, right? Because here xn minus 1 and xn is not a valid bracket. But we already know that the xn is guaranteed to be between xn minus 2 and xn minus 1. So what we're going to do, simply, before continuing with the secant, we decide where the root is. So we test xn with xn minus 1 and xn minus 2. If xn minus 2 and xn is a valid bracket for the root, we continue with this interval. If xn minus 1 and xn is a bracket for the root, we continue with this interval, right? So this way is a better improvement. Or we can say that then secant is guaranteed to converge to the root in this interval. Because if we continue with this and hit the xn plus 1 here, there might be a root around here. So this can in fact converge to this root, okay? So here, to clarify again, so instead of drawing this line from the xn minus 1 and xn, we want to change the code to draw this line from xn minus 2 to xn. And as you can visually see, it crosses the horizontal axis at a point that is much closer to the root than the previous one. So this gives a better convergence to the root that is in fact in the search interval in the original bracket. All right. So let's head to Eclipse. So what I'm going to do, I'm going to go to the real root class, and in the secant method, what I'm going to do here, and instead of just going into x2 x3, I'm look for the valid bracket. So I'm saying that if func.value x1 times func.value x3 is less than or equal to 0, I have to go into the x1 x3 instead of x2 x3. Else if func.value x3 or x2 times func.value x3 is less than or equal to 0, we're going to set the root to secant x2 x3. all right, and then we're going to return the root. So we go into the recursion and then we come back and return the root. If none of them is a bracket, we just return that, okay? And then we can also check for initial bracket. So we can also add this fact that check for the initial bracket. So you want to make sure that the initial interval is a valid bracket. So if func.val start times func.val end is greater than 0, then we don't have an initial valid bracket, so we're just going to return double.nan. Okay, so we're just saying that okay, this is not, we can throw an exception or just return nan. Okay, now let's head to our test class and try to test it. or maybe I'll just create a new class, test secant, and I'm going to write this public static void test1, and here I'm going to run test1. Okay, and let's go back here and try to copy from one of the secant tests, for example this one. So we use the lambda expression for the real root function, and it maps x to x squared minus 2, and I want to find the roots in 0 to 5. Now at 0 we get minus 2, at 5 we get something positive, so this is a valid bracket for the root. Okay, so let's see what happens with the secant method. So it converges quickly to 1.414213, which is the root, right? And if I go minus 5 to 5, this is not a valid bracket, right? Because at minus 5 and at 5 the function is positive. So we end up with a nan, all right? If I go minus 5 to 1, this is still a valid bracket, because at 1 we get minus 1, at minus 5 we get a positive number. So this should converge to minus square root of 2. And as you can see, now we are guaranteed that the secant converges to the root inside the interval. Okay, and that's now because of the fact that we search for a valid bracket when we're doing the recursion. And let's say we put it to 1, x squared minus 1, we return 1, and if I put this to 0, I should get the negative 1 root, which is correct. If I get this to I don't know, 5 and 0, 0 and 5, 0 and 2, this is still a valid bracket for this x squared minus 1, so I should get the 1 root, right? Now we also had now that we improved the secant method, we also had the function that returns all the roots in a given interval based on the number of subintervals. So let's also go and test that. Test 2, we're going to run test 2, and let's stay with x squared minus 2, and then instead of calling this that returns a double, I'm going to return a list of doubles, roots, and let's call this a root finder object, root finder times Brent, which returns number of, so we're going to start with minus 5 to 5 and 100 subintervals. So here we don't care about, let's import the list from the Java util. And then let's print the results. So what we see here is that we don't actually care about whether or not the initial interval is a valid bracket. That's the whole point, because we divide it into subintervals, and then we search that which subinterval is in fact a valid bracket. So we get minus square root of 2 and plus square root of 2. Obviously, if I set it to 1000, the results will be the same, right? Doesn't add more overhead because of this fact. It doesn't go and do the initial search. and because as soon as it sees that the subinterval is not a valid bracket, it discards it. Now we could do the same thing with the bisection and trisection, and we didn't add this thing. We said that okay, in the bisection just go do the recursion. If you don't find the root, then return none. And it worked based on the midpoint. But we can also enforce the fact that the initial interval must be a bracket. So let's try other functions. For example, x squared minus 1. Okay. I think 100 points is still fine. Let's try math.sine of x. It fails. Math cosine of let's call this minus 425. It still fails, and it could be due to several reasons. We have to look into what happens. Let's say x times sine of x. It succeeds in finding the roots. One of the roots is 0, one of is minus pi, the other one is pi. And let's increase the number of subintervals. The same thing, so it doesn't matter, doesn't add more overhead, because as soon as it sees that it's not a valid interval, as soon as it sees that it's not a valid interval, it just discards it. Here in the secant. Okay. Now the question is, so in the Brent we had this in the secant method, we had this test to make sure that the root is actually in the interval, and let's see what happens now if we remove that. Because of the improvement that we made, we are guaranteed that if there is a root in the bracket, we should be able to converge to it. So there is no worry about whether or not it's between the start and end. It's guaranteed to be there. Let's make sure that this happens. Minus pi, and 0. Yes. And let's increase the interval, minus 12. So we get minus 3 pi, 0, minus 2 pi, and minus pi. Okay, so we are guaranteed that the secant method, not Brent, secant. Sorry, I was running the wrong. Now it fails. Let's test with the. So we know that the Brent method works. So let's test with the secant. So the secant is still have some problem converging. And let's see the previous case. It works. -4 from -4.5 to 1000, we get minus pi and pi. Now, interesting thing, it doesn't find 0. It doesn't converge to the 0 term. Maybe let's try with the. Still can't find a 0. Let's say we just have a linear function x. It finds the 0. And I'm assuming that's because the slope of the x times sine of x is maybe somehow. Now we know that the function x times sine of x is an even function. So at 0, it's a tangent root. So if I use, for example, trisection, we might not see this Yes, so in the trisection we don't see the zero term. If it wasn't a tangent, so we know that the trisection is guaranteed to converge if the root is there, right? So here if I use the trisection or bisection, we don't see one of the zeros, which is exactly at 0, because the function is tangent at 0. But secant is also failing, and you can look into the reason why it's failing, but it's not revealing the 0. If I use Brent can in fact find all the roots, 0, pi, and minus pi. So Brent is the most successful root finder so far. And next we're going to look at the Newton's method, which is similar to Brent, but similar is mostly to secant, but it promises much faster convergence if in fact it can converge. So thank you for watching this tutorial. I hope you enjoyed it, and I'll see you in the next video.